Swayam Prabha. Digital India. Educated India.
Welcome to the 23rd lecture on cryogenic engineering under the NPTEL program at IIT Bombay. The earlier lecture, we were talking about gas separation column or a distillation column. The earlier lecture, we have studied temperature composition diagrams and enthalpy composition diagrams, and we have understood the importance of these diagrams in gas separation. The separation of a mixture is more effective when the difference in the boiling points is more. That is also we have understood. In this column, the distillation column, the low and the high boiling components are collected at top and the bottom respectively of the column. For example, in a nitrogen oxygen, you will get liquid nitrogen at the top and you will get oxygen at the bottom of the column. We also defined Murphy efficiency, which is the ratio of actual change in mole fraction to the maximum possible change that can occur in the mole fraction. In a way, it actually points at the ineffectiveness of the column. This can help us to calculate the number of plates or number of processes of condensation and boiling that should occur in the column. In the today's lecture, I will again continue with the gas separation, and what I would like to bring about is a beautiful animation to understand the functioning of rectification column or a distillation column, and then from there just giving a animation so as to understand what all different processes that happen in a rectification column, and then we will go ahead to understand the theoretical plate calculation or actually a design of a plate column or a rectification column. So, let us come to first the animation. I am showing you a distillation column. The animation has been done by Sneha Devrukkar, and this animation has been done under the project OSCAR, which is open source courseware animation repository at IIT Bombay. Please look at this, and possibly you can come to understand different processes that happen when the feed enters the column. Now, in this column, I have shown not the steady state operation, but I have shown different processes that happen in this column. When the feed comes, how the feed gets pre-cooled first before it enters the column, and how the high boiling component and the low boiling component travel up and bottom respectively. So, please see, and each process has been highlighted, and at the end what you see is a steady state operation of this column. So, lot many ideas can get clear how exactly this process happen, because the vapors go up and the liquid comes down. So, you can see this is a column and the process gas, and let us say air, it is coming through this, and this process air comes through this and it goes through something called as boiler. You know about this. Now, as I said, I am just saying process by process and assuming that there is a high boiling component sitting over here. For example, there is a liquid oxygen already sitting over here, and this process air will therefore get pre-cooled in this boiler. And during this pre-cooling, some of the vapors get evaporated and they start coming up, and this process gas then gets expanded through a jetty valve and enters over here at the middle of the column at some location in the column, and the liquid starts coming up over here. And you can see that on this plate, there are various plates, the liquid starts getting accumulated, and once the liquid levels goes to a particular level, it starts coming down to the next plate which is below it. So, you can see that as each and every plate gets filled up to the wear height, the liquid starts coming down, and from the bottom the vapor starts coming up. Because of this pre-cooling, vaporization happens, and the heat transfer happens, as we have already seen, between this vapor which is coming up, and you can see this boiling happening over here. So, the boiling and condensation that starts happening together, the liquid starts coming down, and as the liquid starts coming down, it gets richer in high boiling component, and slowly you can see that the vapors are going up, and this vapor reaches the condenser dome. And you can see that the condenser needs to be cooled by some cooling effect which is supplied by an auxiliary circuit. So, some cooling effect is offered over here, some heat is taken out from here, and whatever vapors come out, it gets condensed over here, and from here what you get is a low boiling component in liquid form. Not all the liquid is taken out, some liquid starts coming down also. In order to have a steady state, you will have some liquid coming down, and what you can see again is heat transfer between the upcoming vapor and the downgoing liquid. And you can see that on each plate there are small holes or bubble cap through which vapors rise up, and the liquid will go down through this weir. So, there is a beautiful animation to understand how the vapors start coming up and how the liquid start going down, and a steady state it ultimately reach as shown over here. So, ultimately you will have some liquid at this point and you will have some liquid on the top of the column, and this is where you understand how this process happens. So, we have seen the animation of a distillation column. We have understood how the vapor rise up, how the liquid start going down, and what is most important is the heat transfer between this vapor which is going up and the liquid which is going down. This knowledge will help us now to understand how these different processes of boiling and condensation happen. That is the most important thing, and based on this we do the distillation column design, and in this case now we are going to talk about the number of plate calculations or how many plates will be required. Again, coming back to some basics, this was a column which we just saw. What you get on the top is a liquid nitrogen or a low boiling component. What you get from the boiler over here is liquid oxygen or a high boiling component, when we assume that the feed is air. So, here you can see now the feed is coming at this point, and as seen earlier in the rectification column, the liquid moving down is enriched in high boiling component. So, as the liquid is moving down, the high boiling component means temperature will go up, and as it goes down from here or as it comes down from here, it will get richer and richer in high boiling component. At the same time, as the vapor is moving up, it will get enriched in low boiling component, which is nitrogen. So, as it goes up, that means it will come down in this temperature composition diagram you can see here, and as it comes down, it will get richer and richer in low boiling component. This is the basic which we have studied in earlier lectures also. What does it mean? It means that for getting 100% pure product, that means if I want 100% nitrogen from this mixture or 100% oxygen to be separated from this mixture, I would need to have infinite number of rectification processes. That means I would like to have condensation and boiling which is happening on every plate. I will need so many plates to be there, and in principle I would require infinite plates, because the heat transfer is never perfect. It will always have some ineffectiveness associated with it. So, in principle we need infinite plates, but in reality the size and the cost of the column limit the number of rectification processes and therefore the purity. So, I will have to sacrifice some purity, that I need not have 100% pure nitrogen, I need not have 100% pure oxygen, but maybe 98%, maybe 97% is good enough for me, and therefore a column has to be designed for a given purity which is a input data. Okay? That is very, very important. So, in order to calculate the number of plates that are required, or in order to design this distillation column, various researchers have developed various mathematical procedures which are very important to calculate the required number of rectification processes. That means how many plates will be required, which will indirectly determine the desired purity for nitrogen as well as for oxygen, and this is what constitute a major design of a rectification column. Now, these procedures require following data. What are number of components? So, your feed should have so many components. If the components are many, there will be difficulty in separation or even in calculation. So, how many components are there? Can we have some reasonable assumption? For example, air, we say that we have got only 2 components. But if you have got 4 components, then the data for all these 4 components in a mixture will be required, and what is essential therefore is a phase diagram of the mixture. So, more the number of component, more important will be to have a phase diagram for this mixture. Also, what is important is the property data of mixture at lower and lower temperature, which is also very, very difficult to get. And ultimately, what is most important is to know the heat transfer correlation, because as you know, boiling and condensation heat transfer is occurring on every plate. So, one needs to have all these correlations, validated correlations for this data, which is very, very difficult. The method of calculation that are used for theoretical plates are, so we have got several methods and we are just naming 3 methods, which is called method of Ponchon and Savarit, which is a first method. The other method is called method of Maccabe and Thiel. It is called Maccabe-Thiel method. and the third is a numerical method. So, these two methods are named after the scientist who developed these concepts or procedures. So, we got a Ponchon and Savaret method, we got McCabe and Thiele method, and ultimately what we have is a numerical method. Now, let us just see what these methods constitute, or what are the required basically in order to get the distillation column design. The Ponchon and Savaret method is an exact method for a plate calculation. It is applicable to any number of components, and this method requires detailed data of enthalpy composition diagrams of the mixture. So, I can have 4 component mixture, 5 component mixture, but what I need is a correct detailed data of enthalpy composition, which is very important and which is very difficult to get also. While McCabe and Thiele method was proposed by 2 scientists, which is McCabe and Ernest Thiele in 1925, and this method is less general and is simplest technique. This is a very simple technique, less general however. Why it is less general? Because it is widely used for binary mixture, that means a mixture consisting of 2 components and at cryogenic temperature. So, this method for binary mixture has been found a simple technique, as well as it validates very well with the cryogenic conditions and cryogenic temperature also. The third is a numerical technique, which, as you know, many of you know now, with the mathematical tools we can have various equations for mass, energy, momentum, etc. that will be solved at every point as the vapor moves up and the liquid comes down. These methods, as you know, are tedious, time consuming and very computer intensive. So, for the sake of understanding in this lecture and in this course, we are going to concentrate on McCabe-Thiele, which, as I just told you, it is valid for a binary mixture and is relatively simpler and also validated at cryogenic temperature. So, we will now see what is this McCabe-Thiele method comprise of. Alright. So, of all these 3 techniques, let us go for McCabe-Thiele and understand how do we calculate number of plates that are required to separate a given mixture for a given purity. That means, if I want to have 98% purity, 95% purity, etc. are the requirement, how do I design a distillation column? So, this is the distillation column, and now let us come to the McCabe-Thiele method. This method calculates liquid and vapor fraction of each component at every plate and also the number of plates. So, what do we do basically? We march up or we march down from the feed. This is the feed. You go up or you go down, and at every plate we calculate what is the liquid and the vapor fraction of each component. And again we are talking about a binary mixture over here at every plate, and also therefore, we will calculate ultimately the number of plates required for a given purity. Now, let us come to the mathematics involved in this. Right? There are various mathematical steps. I have tried to go in details, but you will have to go through that many times to understand all the algebraic derivations involved in it. But what is most important is to understand the physics behind the system. For the sake of understanding, let the plates above the feed, which is called enriching section, be labeled as N. Similarly, the plates below the field, which is what we call as stripping section, be subscripted as M. Alright. Let the total mole flow rate of top and the bottom products be D and B. So, whatever moles we get at top as moles per hour, moles per second, whatever, and what you get here is a low boiling component, what you get at the bottom is a high boiling component. So, let us say we receive D moles per hour and we receive B moles per hour at the bottom. So, let the total mole flow rate of top and bottom be D and B respectively. Now, consider a small plate over here, and you can see that it is important to understand the indexing pattern of the plate and its corresponding liquid and vapor. So, as you know that for this plate, we have shown just 2 plates, and the vapor will leave this plate and it will also receive liquid from the top. So, we have just shown 2 plates where the vapor will go up and liquid will come down. Let us call this as the jth plate, any random plate in this, and this is jth plate and this is a j plus 1th plate. Alright. So, let jth and j plus 1th plate be any intermediate plate as shown in this figure. The liquid and the vapor leaving from the top of the jth plate are therefore called as Lj and Vj respectively. So, consider any plate, jth plate. The liquid which is leaving this plate is coming down over this weir as you saw in the animation, and let it be represented Lj. So, Lj represents the liquid which is leaving this plate, and Vj which is going up, the vapor which is going up, the vapor which is leaving the jth plate be called as Vj. So, for any plate you got Lj and Vj as liquid leaving the plate and vapor leaving the plate. Alright. Similarly, the liquid coming to the jth plate is from the j plus 1th plate. So, this is the jth plate and it is receiving liquid from the top plate. So, what is the liquid which is leaving the j plus 1th plate is Lj plus 1. So, therefore, the liquid which is coming to the jth plate is Lj plus 1 and liquid which is leaving the jth plate is Lj. Please understand this nomenclature because it is very important. So, jth plate receive the liquid Lj plus 1 and the liquid which leaves the jth plate is called Lj. Also, the vapor coming to the jth plate is coming from the bottom. The liquid comes from the top, the vapors come from the bottom. So, what is that vapor which is coming from the bottom? Is the vapor which is leaving the j minus 1th plate. Alright. So, vapor coming to the jth plate from bottom is vapor leaving the j minus 1th plate and therefore, it is called as Vj minus 1. Okay. So, for any plate, let us just revise. For any plate, Lj and Vj are the liquid and the vapor leaving this plate. This plate receives liquid Lj plus 1 and this plate receives vapor which is Vj minus 1. Alright. The vapor and the liquid on any plate Lj and Vj are in thermal equilibrium. We have seen this earlier that for any plate the liquid and the vapor are in thermal equilibrium. That means their temperatures will be remaining the same, that is Lj and Vj. Okay, now let us take a control volume and as we have done, we will do the mass balance and the energy balance, etc. So, consider a control volume enclosing the condenser and top section of the nth plate. So, this is the nth plate and this is the top part of it. So, this is the condenser on the top and let us have any plate, nth plate over here and this is our control volume. Okay. As explained earlier, for this nth plate, the vapor leaving is Vn. So, this is the nth plate and therefore, whatever vapor is leaving up is the Vn and whatever liquid is coming down is Ln plus 1. I think this is very clear now. So, applying the mole balance across the control volume, what we get is now what is coming in the control volume is Vn and what is leaving this control volume is D and Ln plus 1. This is very important to understand again. What is leaving is D and Ln plus 1 and if we do the mass balance now, what we get is Vn is equal to Ln plus 1 plus D. Alright. So, this is the most important. Whatever vapor goes up, ultimately it is equal to whatever condensate you receive at the top and whatever liquid comes down, very understandable. Multiplying the mole fractions, a mole balance equation with mole fraction. Now, this was a molar balance which comprises of both the components. V moles are going up, alright, and D moles are received, but all these moles will have both the fractions of let us say component A and component B. Now, if I want to make a molar balance of only one component of let us say component A or let us say nitrogen for example, we have to multiply by its mole fraction. So, what is the mole fraction of nitrogen in a feed mixture? So, multiply the mole balance equation with mole fraction of a particular component in a mixture, we get mole balance for that component. Now, we are talking about component balance, component mole balance. So, therefore, Yn Vn is the mole number of moles of a component which is going up. So, let us say nitrogen, if I say, so Yn Vn, because I know Yn is a fraction of nitrogen in the mixture. So, Yn Vn is going the vapor fraction, Yn Vn gives the vapor fraction of the one component of this mixture and Xn plus 1 Ln plus 1 is number of moles of that component which is coming down. Okay. And at the same time, Xd into D is the moles of that particular component which is leaving this control volume. So, now we are doing a component mole balance from the earlier complete mole balance. So, where Yn, Xn plus 1 and Xd are mole fractions of particular component in vapor, liquid and top product respectively. Alright. That means, if I got a component Xd which is leaving over here, so Xd actually represents amount of nitrogen in D for example. Alright. It is very important to understand that Xd therefore, if I say I want D is the top product, if I say that this D should have 98% nitrogen, then my Xd becomes 98.98 actually, which is what it says. It automatically means that Xd, which is the mole fraction of a particular component, is the desired purity of the top product. Alright. So, this is basically desired purity of that component in D. For control volume taking into account Qd watts, now we have got a condensation happening out here and therefore, some refrigeration effect has to be supplied and this is Qd. because some heat has to be taken out from here. So, QD has to be taken into account when I do energy balance. So, QD watts as the heat rejected by the condenser, the enthalpy balance is given by, now I am doing energy balance, alright. First we did the molar mass balance, now we do the energy balance and multiply all the component with respective enthalpies and include QD in that. So, what is the energy of the moles Vn which is coming up? HnVn is equal to the liquid moles which are coming down and therefore corresponding enthalpy of small h. We know about this. We have seen the enthalpy concentration diagram, enthalpy composition diagram. So, small h denotes the enthalpy associated with liquid, the capital H shows the enthalpy associated with vapor. So, HnVn is equal to Hn plus 1 Ln plus 1 plus HDD, which is the enthalpy associated with the top product, plus QD. So, this is entering and all these are leaving and therefore, the energy balance has been done. Now, do the mathematical jugglery and therefore, we have some algebraic rearrangements over here. Dividing above equation by D, what you get is this. So, you got a now D at the bottom over here. Rearranging the total mole balance equation, we have already got a total mole balance which was this, and if I rearrange that or divide that by D, I will get expression. So, what is important to see here is you got Vn by D over here, you got Vn by D here, you got Ln by D over here, you got Ln by D over here. So, if I replace this Ln by D by this, you will get a further expression. Just put these values over here and eliminating Ln plus 1 by D from the earlier equation, what you get is this. So, now you got a two terms which has got Vn by D common, and doing that I will get an expression like this, taking capital H and small h difference, that is the enthalpy difference between the vapor and the liquid, Vn by D, and you got all energy terms over here. So, here I can rearrange the whole thing and get D by V as this expression. What does it mean? What is D? It's the moles of a top product coming out, and what is Vn? The moles of in vapor form which is entering the control volume. So, D by V actually represents something. Vn is entering the control volume, D is leaving the control volume. It's a condensed low boiling component which I am getting. So many moles I am getting at the top, and it depends on the enthalpy difference between the vapor and the liquid, and you got all the energy terms coming over here, QD, HD and Hn plus 1. So, all the enthalpy terms plus the cooling effect that has been supplied coming over here, and this gives a very important term called D by Vn. Now, let us see the enthalpy terms. You know the enthalpy composition diagram, enthalpy and mole fraction diagram is shown like this. The enthalpy composition diagram for a mixture of nitrogen and oxygen, let us say at 1 atmosphere, is shown over here. So, this is vapor and this is liquid, and there are different temperatures. Knowing that, we know the change of phase is not at constant temperature, all right. If we neglect enthalpy variation with the mole fraction, the bubble and dew lines can be taken as horizontal. These are the bubble and the dew line. And now, understand from here, you got some inclination over here, and can they be approximated? Can they be approximated? You can see that enthalpy changes with mole fraction, but can I say that we can understand that change in enthalpy is not so much over here, it's not so much. So, understanding from that, you can see that this is this. If I approximate as a straight line, I can come to a conclusion that now both the enthalpies are independent of mole fraction, and if I do this, matter become very simple for me. So, now coming back to the expression, you got this, and if I say that, and also one more expression, and the argument which we just did, that it leads to the fact that liquid enthalpy, vapor enthalpies are constant, they are independent of the mole fractions, and hence we can say that because they are all enthalpy dependent, and if we say that they do not change at all, we can say that D by V and therefore L by V is constant. These terms are constant. They will not change from plate to plate because the enthalpies will remain constant. They will not change with molar fraction, which is what happened from every plate, right. Please understand this concept. So, we come to the conclusion therefore, that both D by V and L by V are the terms which are constant, and if I rearrange my mass balance expression early, I now get an expression which is Yn is equal to Ln plus 1 by Vn Xn plus 1 plus D by Vn Xd. So, here we have got two components which is L by V and D by V, and both we have just proved that they are constant. What does it mean? What does this equation tell you? Y is equal to mx plus some constant term. So, it is basically an equation of straight line, and that is with this assumption we are leading to this conclusion that this represents an operating line for the top section of a column, which will give me what is the vapor fraction at every corresponding to that vapor fraction, I will get what is the liquid fraction. So, I can now calculate y and x at every location in the top section, and this is what we were aiming for. The above equation represents a straight line and is called as operating line for enriching section, gives you a relationship between y and x, vapor and liquid at every stage, and this is what we wanted to do basically when I told about what do we basically aiming for in a design of a rectification column. So, this is an expression which we have just derived. Also understand that at the topmost plate I got xn plus 1 is equal to xd at the topmost plate. This is xd which is coming at condensate, all right, because there is no other plate, and at the topmost plate the purity is going to go on increasing and this is equal to xd. Substituting this value xn plus 1 is equal to xd at the top plate, what do we get? I just replace xn plus 1 as xd. I get, if I put the value of xd taking common and if I put the relationship between these two, this is nothing but equal to 1. So, what do I get? Yn is equal to xd. What does it mean? For the topmost plate, yn is equal to xd, not for any other plates, only for the topmost plate I get y is equal to xd. And what is this intercept of this line? So, we have located one point on the top which is at the topmost plate, and other point if I want to draw this line is the y intercept, and this is nothing but the y intercept d by Vn into xd, and this will happen when xn plus 1 is equal to 0, and that is why it is called y intercept. So, we have got a yn is equal to d by Vn xd, and therefore, what I conclude from here, I know 2 points to draw this operating line for a enriching section. What are these 2 points? Yn is equal to xd at xn plus 1 is equal to xd, which we just derived, and also the other point is the y intercept, which is yn is equal to d by Vn xd at xn plus 1 is equal to 0. So, if I know these 2 points, I can draw the operating line for the enriching section. If I want to do that now, I am plotting y versus x for a component, let us say a component. So, a plot of vapor versus liquid mole fraction for a particular component says a is as shown in the figure. So, what I do first, I will just draw a y is equal to x line, okay, because I know that y is equal to x for the topmost plate. What I also know, the desired purity of this component A in the top product is xd. This is the problem definition for me, that I want to design this column for getting a purity of xd for the top product or for the low boiling component, all right. So, I can locate this point which is xd over here on the x axis, and if I want to locate that point on this scale, I got this equation, and as you know, I got other point which is at x is equal to 0, I got a y intercept. So, what are these 2 points? The first point is this, y is equal to x. So, yd is equal to x, yn is equal to xd, I can locate on this, I am sure, because it lies on the y is equal to x line. So, locate this point, the other point is this, and if I join these 2 points, I will get the operating line for the enriching section. I will know how much y is there for every x at every location in the enriching section. Okay. So, if I know my x is this much, corresponding to that I can calculate y, which is also given by this operating line equation for the enriching section. What I am doing ultimately, with some reasonable assumption, I am trying to get the liquid and the vapor at every plate in the enriching section, and now I will do the same exercise for stripping section also. That means, for the bottom part of the column also. This is what we are aiming for basically. Similarly, the slope of this operating line is L by V, all right. The slope is basically how much liquid is coming down, how much vapor is going up for every plate. We are saying that the slope of this line is same. That means, what we assume is L by V is common for the entire enriching section. Okay. This is what, there are some reasonable assumption, and that is why we say that with enthalpy remaining constant, this will automatically come. Now, what we are concentrating on is the bottom part. So, if I take a control volume for now enriching section, similarly for the analysis of mth plate and boiler in the lower part, we have the following equations. So, what is the mole balance now? Lm plus 1 is entering. So, I have got a mth plate over here, and I am taking top of mth plate and the boiler over here. We have got what is entering is equal to what is leaving. So, mole balance is Lm plus 1 is coming down, Vm is leaving this plate, and B is leaving this control volume. So, if I do mole balance, for entire mole balance for both the components, Lm plus 1 is equal to Vm plus B. And then if I do component balance as we have done earlier, for a given component A, I will have Xm plus 1 into Lm plus 1 is equal to Ym Vm plus Xbb. Again Xb is now denoting how much A is there in bottom. As you know, Xd we are assumed to be 98%, but Xb is now going to be very small because I do not want this nitrogen to be there in oxygen. So, Xb is going to be only 0.02, 0.03 etc., right, because the purity of B has to be 97%. And I am talking about component of nitrogen in oxygen here, and that is what Xb will denote, because we are doing mass balance for the same component over here. The third is the energy balance multiplied by enthalpies, and also I am giving some heat to this boiler, that also would figure in this, as it had figure Qd in the condensation in the earlier case. So, if I do enthalpy balance, HmLm plus 1 plus Qb, which is entering the control volume, is equal to HmVm, which is leaving over here, and HBB, which is leaving the place, all right, where B and Qb are the mole flow rate out of the bottom and heat input to the boiler respectively. Now, I will do the similar rearrangements as what we have done in the earlier enriching section. Rearranging the above equations, we have the following. I will get B by Vm is equal to Hm minus Hm plus 1 divided by Qm upon B minus Hb plus Hm plus 1. And again we have got a similar assumption that enthalpy values are independent of the molar fractions. We can again show that B by V is constant, and therefore, Lm by Vm also will be constant. Applying the assumption, we have capital Hm and small hm plus 1 as constant, which implies that B by Vm and Lm plus 1 by Vm are constant. The operating line for the stripping section therefore is Ym is equal to Lm plus 1 by Vm into Xm plus 1 minus B by Vm into Xp. So, similarly, what we had done earlier, I have got an operating line for the enriching section, which will be giving me amount of vapor for every X, amount of vapor for liquid on every plate as we march down. Okay. And this L by V is going to be the slope of that line, which is constant throughout, and this is the Y intercept. So, again if I want to draw this line graphically, I have got 2 points, which is what we will see now. So, this is my expression for the equation of line for the stripping section. Again putting the same assumption, for the bottom or the lowermost plate near the boiler, we got Xm plus 1 is equal to Xp. It basically shows how much nitrogen is there in oxygen, which is going to be a very small amount, all right. It is going to be 0.02 or 0.03. It actually talks about the impurity now for the down product, and which is the purity for the top product. Substituting in this value, so if I write this equation only for the bottommost plate, I will get Xm plus 1 is equal to Xb in that case. Putting that, I will again get an expression as 1, and I will get a Ym is equal to Xp. That means, this line again has Ym is equal to Xb or Y is equal to X at the bottommost plate. So, again this line will intersect Y is equal to X line at the bottommost plate as we saw earlier. This is one point I will get. Another point again is a Y intercept, which is minus B by Vm into Xb. So, other point is a Y intercept, which is definitely going to be at Xm plus 1 is equal to 0, which is the Y intercept. So, again I have got 2 points, which are Ym is equal to Xb at Xm plus 1 is equal to Xb, basically the intersection point of the operating line at Y is equal to X, and other point is the Y intercept. Ym is equal to minus B by Vm Xb at Xm plus 1 is equal to 0. So, now I have got two operating lines, and I will draw those two operating lines graphically. So, this is my earlier line, which is operating line for enriching section, the plot of vapor versus liquid mole fractions for a component A with operating line and 45-degree angle as shown over here. The purity of the component A in the bottom product is Xp. So, what is the purity now? Actually is going to be impurity for this product. It is going to be 0.02. How much of component A exists over here is going to be Xp, which is very small. So, if I locate that and now locate this point on a Y is equal to X, because at this bottommost plate, it is going to be, the Y is going to be equal to X. So, it is going to be on a Y is equal to X line, all right. So, other point is going to be the Y intercept, which is minus B by Vm into Xb. This is this. So, one point is going to be here, other point is going to be here, and I am just going to draw this point. So, this is my one point, another point is this. So, if I draw a line between these two, I will get operating line for the enriching section, and this is my operating line for enriching. So, this line gives me what is y for every x in the stripping section, and what does this line give me? What is my y for every x in the stripping section, and what does this point indicate? This point indicates where both of them meet, and this is something called feed point, where the feed inlet happens. The slope of the operating line is given by Lm by Vm as shown in the above expression. So, now after seeing that how these operating lines for stripping section as well as for enriching sections are drawn, now we will come to the third point, which is third line, which is called the feed line, which will denote the feed condition for the column, and this is very important because this is the point at which both these lines intersect. The mixture that is to be separated is called a feed. It is introduced in the column through an opening called as feed inlet as shown in the figure. So, you can see here F. This F denotes this is the feed inlet through which the mixture enters, and this feed point could be anywhere. It need not be at the center of this column. It can be at this point, at this point, depending on the feed condition. This feed inlet can vary. All right. Now, let us consider a control volume across this. Till now, we had a control volume including the condenser, or the other control volume we had including the boiler, and that was above the feed or below the feed. Now, let us take a control volume which encloses some part of some plates in the enriching section and some plates in the stripping section. So, you got one N plate and one M plate over there, and let us do again the mass balance and the energy balance, and the difference of this is going to come from the feed, because inlet is feed, what is leaving here is going to be N, what is leaving here is going to be M. So, consider a control volume including the Nth and Mth plates and feed inlet as shown over here. Let F be the number of moles in the feed. So, the total number of moles that are coming are F. Let us see the control volume like this. So, you got a Nth plate and you got a Mth plate, and you got a control volume as shown over here, comprising of, let us say, just two plates above near this feed. So, what is coming in the control volume and what is leaving the control volume? Have a look at this. So, the above control volume we have what is in is feed inlet, which is F. What is entering from this Mth plate is Vm, all right, and also what is entering from the top here is Ln plus 1. This is the Nth plate one, Nth plate. What is entering this Nth plate is Ln plus 1 liquid. So, what is entering this control volume is F, Vm and Ln plus 1. F, Vm and Ln plus 1 are entering the control volume. And what are leaving control volume? What things are leaving the control volume is Vn, which is the vapor which is leaving the Nth plate, and the liquid Lm plus 1 which is leaving or which is entering the Mth plate. Okay. So, this is Ln plus 1 over here, and this is Vn which is leaving. So, if we do the mass balance or the molar balance of all these components, what you get applying the molar balance, what you get is equal to F is equal to Vn minus Vm plus Lm plus 1 minus Ln plus 1. Have a look, is F is a number of moles that are coming in the feed, difference between the vapor component which is Vn minus Vm, difference between the liquid component what is Lm plus 1 minus Ln plus 1, all right. Very important to understand that this is the feed, and we can have the feed can have some vapor component as well as some liquid component. So, what is the vapor component? Vn minus Vm. What is the liquid component? Lm plus 1 minus Ln plus 1. Sometimes vapor may not be there, so only liquid component could be there in the feed F. That time Lm plus 1 minus Ln plus 1 is equal to 0. Sometimes only vapors can come in the feed, and that time Lm plus 1 minus Ln plus 1 could be equal to 0. All right. So, feed conditions will decide what is the form. It has vapor plus liquid, only vapor or only liquid, and that will decide what we call as feed quality. All right. So, please have a look at these things. So, if you come to the same thing again, we define a parameter called Q. All right. We define a parameter called Q, which can denote the quality of the feed also. Okay. Q as the ratio. How do you define Q? It is the ratio of liquid moles in the feed to the total number of moles in the feed. So, how many liquid moles are there in the feed is called as Q or the quality. What does it actually denote? It actually denotes how many liquid moles are there in the feed. In short, it actually shows the wetness fraction of the feed. How much wetness is there, how much liquid is coming with the feed. So, it is a ratio of liquid moles in the feed to the total number of moles in the feed. So, mathematically if I want to write Q, Q is equal to Lm plus 1 minus Ln plus 1 upon F. If we just saw the definition earlier, the liquid components are going to be given as Lm plus 1 minus Ln plus 1, and therefore, Q is equal to what is amount of liquid moles to the feed, number of moles coming in the feed. It also denotes something. If I have Q is equal to 0, that means Lm plus 1 minus Ln plus 1 is equal to 0. That means there are no liquid components in the feed. What does it mean? If Q is equal to 0, the feed is completely vapor, because your numerator is going to be 0 and no liquid moles are coming in the feed. So, if Q is equal to 0, your feed is completely vapor, or if Q is equal to 1, that means Lm plus 1 minus Ln plus 1 is equal to F. That means feed is 100% now liquid, F upon F, and therefore, you got Q is equal to 1. It means therefore, that the feed is completely liquid. So, got a meaning to the value of Q. If Q is equal to 1, it is completely wet, that means it is only liquid, it is bringing only liquid, and this liquid could be saturated liquid. If Q is equal to 0, the feed is bringing in only vapor, and if something in between, then you got some V and some L also. That means you got a two-phase feed now, you got a vapor and liquid component also. We will study that in detail in the subsequent slides, but understand the concept of Q, because very important. So, this is what we have already studied, that we have got operating line for the stripping section, we got operating line for the enriching section. From the earlier slides, we know these equations for both these sections. Now, you got the intersection point, and the locus of intersection of this operating line denote the feed condition. So, where do they meet? At this point, and they can meet anywhere depending on the slope of these lines, and therefore, slope of these lines also play a very crucial role. The point of intersection, however, will denote the feed inlet condition. All right. The condition of the feed is vital to determine the number of plates. So, what is this locus? This locus could be like this, the feed line could be like this, or anywhere in whatever direction. And this is very important to understand how many plates are going to be there in the enriching section or in stripping section. This plays a very vital role in this. And how does it? So, let us see. Based on the feed equation and Q definition, we have got a feed equation, F is equal to something, and we have got a Q definition also, which is Lm plus 1 minus Ln plus 1 divided by F. What we have is, this is my F definition, this is my Q definition, and if I want to calculate from here, Vn minus Vm is equal to, and putting this value as Lm plus 1 minus Ln plus 1 upon F, I get an expression like this, which is Vn minus Vm, the vapor difference, vapor mole difference is equal to, I am representing this vapor mole difference in terms of Q and F, 1 minus Q into F. Again, from the operating lines of upper and lower section, we can rearrange to get Vn and Vm. So, I can get Vn and Vm from the feed line or the feed expression for the feed, and I can also get expression for Vn and Vm as this, because I have already got equation as Yn is equal to Lm by V and etc. I am just rearranging that to get the value of Vn. So, Vn is equal to L by Y xn plus 1 plus d by Y xd, and similarly I will get Vm is equal to Lm plus 1 by Ym xm plus 1 minus b by Ym xb. So, I got two expressions for Vn and Vm, and from here it is very important to note that Vn minus Vm is the vapor content in the feed. We have just seen that thing. So, Vn minus Vm is going to be the vapor content in the feed if we are writing this equation for the nth and mth plate, what we have defined earlier. In the calculation of point of intersection, now if I am very keen to know my feed inlet condition, which is denoted by the point of intersection of these two operating lines. So, operating lines will have some coordinate x and y, and they should be satisfied by both this equation of operating line for the stripping section and also the operating line for the enriching section. So, we choose a common point and let us call it as x and y. So, hence now we do not have to write xn plus 1, xm plus 1, ym and yn, they will be replaced by x and y over there. And now I get Vn minus Vm is equal to Ln plus 1 minus Lm plus 1 upon y into x plus xdd plus xbb by y is equal to 1 minus q into f. The locus of this point of intersection is the feed line or q line and is calculated as explained in the next slide. So, here for a column as a whole, using mass balance, we can now have an entire molar balance for the column, which is xff is equal to xgd plus xbb, right. These are the moles coming in, these are the moles leaving the column. Again q is equal to ln plus 1 minus ln plus 1 upon f. Rearranging this term, you get this expression. I will replace this by this and this by q. I got this expression, and rearranging this expression, I will get an expression as y is equal to q upon q minus 1 x plus xf upon 1 minus q. This is also a constant, this is also a constant, and this line therefore is called as feed line actually, which has the above equation represents a straight line with q upon q minus 1 and xf upon 1 minus q as slope and y intercept respectively, and it will pass through the point of intersection of the two operating line. So, we got three lines now. One is operating line for stripping section, operating line for enriching section, and this is now what we call as feed line. More importantly, it is the locus of the point of intersection of operating lines. This line is called as feed line or q line. So, we got a third line now, which represents the locus of the point of intersection of the operating line, but it has got a lot of physical significance, which depends on the value of q or the quality, or as I said, weightness of the feed, and let us see how it denotes that thing. So, this is the column. It is clear that the value of parameter q is yet to be determined. Applying the energy balance to the control volume here, I got enthalpy balances for everything. HFF is equal to Vn Hn minus Vm Hm. So, I got enthalpies associated with this. Rearranging this, and we say that all enthalpies are same, or capital H is equal to H, all small h is equal to H. Putting them together, I will get this expression, I will get this expression as again rearranging the term, and ultimately I know also Vn minus Vm is equal to 1 minus q into f. I know the quality expression or q expression basically. Putting these values over here and putting this value over here, what I get q is equal to h minus hf upon h minus h. So, this is enthalpy difference. H minus h is a complete enthalpy difference or the latent part of it, or difference of enthalpy between dew and the bubble point, and this is the feed enthalpy. Hf is the feed enthalpy, which will determine what is the q. Otherwise, this h and this small h are constant. All right. So, this q will be determined what on the fact what is the enthalpy of the feed. So, this is our enthalpy composition diagram, and we know q is equal to h minus hf upon h minus h. Also, we know that the slope of the line SLP is equal to q upon q minus 1, this slope of the q line or the feed line. Depending on the feed condition, q can take any value. So, depending on the feed condition, hf will be determined, and depending on hf value, q will be determined. So, now we have got a feed at various possible conditions. Various possible conditions will decide the value of hf, and which will decide the value of q, which will decide the value of slope of the q line. Let us see those conditions. The first condition is the feed is coming at saturated vapor. In this case, hf is going to capital H, and this is the point, this any point on this line is going to define the saturated vapor condition. If I put hf is equal to capital H over here, I get q is equal to 0, and if I put q is equal to in this line, I get slope as equal to 0. Slope of the q line, slope of the feed line is going to be 0, which means it is parallel to x axis if I plot in a graphical way. Second point is, if I got a saturated liquid which is coming with the feed, so everything is liquid, and therefore hf is equal to small h, and the line will be at this point, the feed line will be, the feed point will be somewhere on this line. If I put hf is equal to small h, I will get q is equal to 1, and if I put q is equal to 1 in the slope, I will get slope as infinity, and infinity line therefore will be parallel to y axis. So, if feed line, if feed has saturated liquid, it will be, the line will be parallel to y axis. If I got two phase now, my hf will be somewhere between h and h, and therefore q will be somewhere between 0 and 1, which can be calculated from here, and the slope will be negative if I get the value from over here. Similarly, if I got a subcooled liquid, that means hf is going to be less than small h, I got a q is equal to now more than 1, and therefore the slope will be now a positive quantity. So, line direction will denote a positive slope. Similarly, if I got a superheated vapor, I got feed point somewhere over here above capital H enthalpy, Q is less than 0 and the slope according to this equation will be positive slope. And if I want to now denote all these conditions graphically, please understand this, it will look like what I show in the next slide. The equation of feed line therefore is this is what we know, and Q upon Q minus 1 is the slope and this is my y intercept. So, if I condition saturated vapor condition, we have already seen that Q is equal to 0, slope is equal to 0 and therefore, feed line is going to be horizontal to x axis, alright. If I got a saturated liquid coming, my slope is infinity and therefore, feed line is going to be parallel to y axis. If I got a two phase flow, I got a slope which is going to be negative, the feed line is going to be passing through this point and in this direction, and subcooled liquid will be shown by this, and superheated vapor is going to be shown again by a positive slope. And therefore, this point or this Q line makes a very big impact in determining number of plates for the enriching section and for the stripping section, which we will see in the next lecture also. So, this is a graphical representation of all the possible line, stripping section, enriching section, and one of these line will constitute a Q line or a feed line for your problem. The point of intersection also what we of interesting is where does this line hit y is equal to x. Okay. The point of intersection of the feed line or Q line and y is equal to x, it gives the liquid content of the component A in the feed xf. How do we conclude this? So, let us find mathematically, it is calculated by substituting y is equal to x in the feed line. So, if I put x is equal to y is equal to x in this, what you get here is nothing but x is equal to xf. By rearrangement, I will get x is equal to xf. It means that when this Q line, wherever it hits y axis, y is equal to x line, you get corresponding to that is your xf. That means, amount of component A, the liquid content of the component A in the feed is given by this line. So, I know now 2 points. If I want to draw the feed line, I know the liquid content of a component given feed, I can locate this point. Also, if I develop equations for the two operating lines, I know in point of intersection, and joining these two will give me what is the Q line, what is the equation also for the Q line or the feed line. So, I know all the equations, I can plot them graphically, and this is what I wanted to cover in this lecture. So, graphically it is clear to draw a line through these two given points rather than using a given slope and a point. So, I get 2 points basically over here. This intersection point is used to draw the feed line as given in the figure. So, I got 2 points, join these 2 points, what I get is a Q line or a feed line. So, summarizing what I have just talked about in this lecture, the plate calculation procedures require the data like number of components, phase diagrams, property data variations of mixtures, heat transfer correlations. McApthil method is less general and is widely used for binary mixture at cryogenic temperature, and this is what we are going to study in this particular topic. The major assumption in this method is that the liquid and vapor enthalpies are independent of mole fraction, and that is what simplified various calculations. The equations of operating line for stripping and enriching sections are this for the enriching section and this for the stripping section. The locus of intersection of this operating line denote the feed condition or the Q line or the feed line. It is given as this, which denotes basically the equation for the Q line or the feed line, and the point of intersection of the feed line or Q line and y is equal to x gives the liquid content of a component in the feed xf, which is what just saw in the last 2 slides. And this is what our graphical representation of all the 3 lines are, and this is what the slope of the line, and this is what we understood. Depending on the feed conditions, you have got various value of HF, which determines the value